What we're doing basically is developing tools for the analysis of medical images. Specifically, we look at the brain mostly. So the brains are imaged on a scanner, whether that's an MRI scanner or a CT scanner, and the images are brought to us to evaluate them. So this is not something that a radiologist does by simply looking at the images, but it's about extracting information that is more than just visually can be seen in these images. So for example, a volume of a certain structure that might change over time and gives us information whether that person may have Alzheimer's or not. Since we're computer scientists, so we are actually programming mathematical algorithms that then read in these images. They extract a certain value, a certain measurement, and then give that measurement back either visually but also quantitatively in order to be analyzed by a statistician or by a clinician. There's many things we do nowadays that have not been possible before. We started basically just looking at images of the brain and trying to understand where is white matter, where is gray matter, and where is this fluid that nourishes the brain, the cerebrospinal fluid. That were basically the earliest ways to look at the brain, and not even looking at this in any pathology, but first trying to understand, can we actually evaluate the brain, these brain images, with any kind of pattern recognition algorithms that we were using that back then. That's maybe 10 years ago.
So the reason that we need the curved space is that the shape differences and the shape changes that occur in the brain occur locally. There's twisting and bending. There are small structures moving on one side of the image and while things are fixed on the other parts of the image. And so it also allows you to measure these local deformations. So it's changes in one part of the brain, twisting, bending, things that you couldn't capture with a rotation or a translation. And finally, it allows you to put essentially a measuring stick in this curved space.
And nowadays we are going more towards actually looking at the fine details of the brain. So nowadays we have algorithms that can take out of the brain certain structure that have certain function. Let's say the hippocampus, which is implicated in schizophrenia, in epilepsy, or in Alzheimer's disease, to be different. We can measure the volume or even the shape of the hippocampus and compare that. That's something totally new that we wouldn't have been able to do 10 years ago.
What I'm showing here is a 3D rendering at the top, but on the bottom, this is actually a slice that's taken out of this image of the average. And there you can see more of the deep structures.
Looks kind of like an MRI slice.
Exactly.
But it's also not an actual MRI slice, but an average MRI slice. When one starts to analyze these images, one first tries the most simple tools, and that's usually tools that are based in linear geometry, and you can only get so far with linear geometry. Because our brains are very different from person to person, we often then need to go to a non-linear space. As soon as we want to use something like that, we need to have non-linear geometry. So we need to go basically from a level of mathematics that we started out from to a higher level of mathematics, basically, that we're using nowadays. Non-Euclidean geometry or non-Euclidean analysis gives us just more detailed information. It's simply not possible to do in a Euclidean way, because the space that we're operating on is a hyperbolic space. So it's very easy, if you just would try to apply Euclidean geometry, to step out of the space of valid results. For example, if we look at shape analysis, where we actually try to describe certain parts of the brain, let's say the hippocampus, and we try to describe it, how is it shaped, all of that basically, whether that's now with the description of the interior, which we use with a skeletal description, or the description of the exterior, which we use as a surface description, we all both need, for these things, non-Euclidean geometry. In the surface, we go to a spherical geometry, so we do everything on the sphere. For the medial description or skeletal description, we actually need to go to a fully Riemannian space and do all our analysis in the Riemannian space. So non-Euclidean geometry gives us new insight because it allows us to see differences, let's say, between one person and the other, looking at the brain, not just in a linear fashion, but we really need to be able to do that. And it kind of like is a must for our research nowadays. What I really love about my work is really that, it is multifaceted. The other thing, of course, that's really inspiring is that we're helping people. that the goal of what we're doing is something that's towards medicine that then actually will be applicable.
Flat surfaces and lines, spherical surfaces and lines, and two types of geometry to go with them. But the curved world and a curved universe don't stop with spherical geometry. What worried Gauss the most about throwing out Euclid's fifth postulate was that if he ended up with a geometry that admits triangles of greater than 180 degrees, it would also be logical that there should be a geometry that admitted triangles of less than 180 degrees. Bolyai and Lobachevsky came to the exact same conclusions, and we now call the geometry described by them and Gauss hyperbolic geometry. Let's see if Dinah can help us see this world too. Now those were some beautiful virtual hyperbolic planes, hyperbolic structures, but you're going to show us, in fact, that these are really tangible things and beautiful.
We can have something tangible. Like, for example, we were seeing something about the circle. We are having a circle with a certain circumference in Euclidean plane.
Right.
And then the circles, we were talking about the circles on a sphere. Now, this is a crocheted version of a so-called pseudosphere.
A hyperbolic surface.
Yes, that's a hyperbolic. That's a hyperbolic surface. This is what is characteristic for a hyperbolic plane. It's like it's really connected with an exponential growth.
That's right. So on a flat surface, we know that if you have a circle of radius r, then the circumference is 2 pi r, so that the circumference grows what we would say linearly.
Yes.
Right? But here,
yes, that grows exponentially.
That's right.
Now let's go back to our old friend triangle.
That's right. The triangle that we've been using to show the differences between all the geometries.
Yes, we know very well. Now, how do we get a triangle on this hyperbolic plane?
Right.
Which is essentially, think about like a piece of paper. And now, to get a straight line, we can simply fold it like we would do it with a Euclidean plane.
Right.
So we fold it. We fold it, so that's straight.
One straight line.
So then we can fold another one.
Another straight line.
We are getting a triangle. And we see these angles. Just visually, we can see that these angles are much less, you know, like they are becoming thin. And even more, what's happening is that if we are having a larger piece, and then we are trying to fold it,
that's right. So
and
now
letting them
now we're extending it.
Yes, think about them that they are extended longer and longer.
Right.
So then we even get so-called, which is called like so-called ideal triangle.
Ideal.
That means
if we had extended it to infinity,
if we extended
if
we extended all three sides to infinity, we are getting ideal triangle where the limit of the sum of interior angles goes to 0.
And so what about parallel lines in this world? Is there anything special
about
those?
Well, yes, there is something, and that is sometimes used, and this is something which was with Nikolai Lobachevsky and Janusz Bolyai when they were talking about that in a space there is a geometry where we can have a line. Here we have a straight line.
Yep. Yes.
And then we can have more than one line which is parallel to the given line. And let's see how it happens. That we can fold the line, and we can see that this line, well, what do we call parallel? Now we have to think about it now. These lines won't intersect.
Not even out at infinity is the point.
No, that's the point, that these lines won't intersect.
Right.
So, and these are non-intersecting lines.
Right.
Yeah, so that's what we call parallel lines. Yes,
non-intersecting lines, but the point being that they all go through this point.
Yes.
Yes.
Exactly.
I mean, that's the important thing.
We can see that these ones, like for example, here there are 3 lines going through the one line, but none of them intersects.
And they're all parallel to this. Whereas in the plane, we know that if you have one line and you take a point off the line, then there's only one parallel line that goes through it.
That's another difference between the geometries. That's a different behavior.
That's right.
And this is something where our intuition, we don't have intuition about it.
Right.
And that's about like the same thing about these other shapes, which is, I have met other scientists, which they are seeing something in their lab, which looks like
something clicks, is that right?
Something clicks, and they say, oh, this looks like, some of the mushrooms. Or there are some...
sea anemone, for
there are sea anemones, there are nudibranch. You see the shape, and you had... and they say, well, we didn't know. We have to use hyperbolic geometry. And that's when the visualization is of help.
So let's summarize and sort of take our tourist triangle on these 3 different geometries, right? So let's see. So the flat one, there's our friendly triangle, 180 degrees, no problem. Now he's going to wander off into positively curved space on the sphere, and he fattens himself up and more than 180 degrees, and then he slouches off to hyperbolic space, and he's thinned down, slimmed down to less than 180 degrees. Well, Dinah, thanks so much, and in particular, thanks for showing everybody how truly beautiful mathematics is and can be.
Thanks for hosting me. I'm glad to be here. Thank you.
To get a picture of the hyperbolic plane on a larger scale requires some mind-bending ingenuity. One way to visualize this enigmatic space was developed by the great mathematician Henri Poincaré. This is a Poincaré disk, a mathematical model that's a map of the hyperbolic plane, where the plane is compressed into a disk. Now, remember, a hyperbolic plane has points that are infinitely far away, and in the mapping of the hyperbolic plane to the disk, the points at infinity become the circumference. The effect of this is that long distances in the hyperbolic plane get squashed in the Poincaré disk. So as I move away from the center in the Poincaré disk, approaching infinity, I'm actually moving exponentially far. Here's another way to look at it. Let's make a beautiful pattern on the disk. If we start with a Euclidean plane and tile it with a pattern, what we have is a repeating pattern that is reflected across straight lines. Now, let's take another butterfly and build the analogous pattern with it in the Poincaré disk by reflecting that pattern across straight lines in the disk. See what we get? The model Poincaré gave us is obviously useful to artists like Josh Leys, whose work we're looking at here. It's useful because it's what mathematicians call conformal. That is, you can measure the angles in the plane and they're the same in the disk. Because it's bounded by the circle, the design can be viewed in its entirety. Poincaré's model offers a precise, aesthetically pleasing way to depict diminishing and exponentially increasing figures within a circle. Through its effect, we see an illusion of negative curvature on this two-dimensional surface. Leys' work, like that of the 20th century Dutch artist M.C. Escher, who inspired him, has produced hypnotically intricate patterns of images that seem otherworldly. And in fact, the hyperbolic plane lies outside the daily experience of the physical world. Or does it? Dinah Tamina's models of a surface with constant negative curvature not only show us what these surfaces look like, they also give us clues about how to find hyperbolic geometry in the natural world. It may have taken mathematicians 2,000 years after Euclid to discover hyperbolic space, but nature discovered it millions of years ago. It's embodied in the structures of marine animals like sea slugs, flatworms, and nudibranches. When Gauss realized that mathematics could see beyond Euclid, it opened myriad possibilities. It's all about seeing ourselves like a bug on a curved world. You could say that, like the bug, we're prisoners of the space in which we live, unable to break free and observe the universe from the outside. But new geometries are giving mathematicians the ability and the tools to figure out things like the structure of space and the shape of our brains, or even the shape of the universe.